Hey students, I thought I'd start another one here. Let me point out that this is chapter 23, number 59. I guess I need to look this up. I should have done this before I started the video camera. Hang on here. There's number 59. And it's a really hard problem. I just want to emphasize that this is a extremely challenging one. In fact, it's one that I decided not, I'll say it again, not to include on the homework. So I was a little taken back by it when I got a question about this one. I was like, wait, I don't think that one's on the homework. This is really a hard one here. And anyways, the student asking the question really wanted me to do it, so I go, okay, well, I'll work through it. I might not make the final steps. In fact, they didn't want me to. They wanted me to just set up the problem, so I will. And then I'll just send it to all of you. But just know this, that this is a hard problem. So if you don't completely follow it or you're too busy on other things, that's fine. This is not a homework problem. This is just extra and above the call of duty here. So let me kind of lay out problem number 59 here. It says 8 charged particles with a magnitude of Q are located in the corners of a cube of edge S as shown in our figure. Now, for those of you who've done the homework, this is actually the same figure for number 60. So number 60 is a homework problem in it, and it looks something like this. It's got a cube. If I can kind of draw a three-dimensional cube here. It's on a flat piece of paper. All right, and so picture a cube, and it says that each corner of the cube has a charge of Q. And so the 8th one is back here on this corner. And the figure shows this extending out as the x-axis, extending over here to the right as the y-axis. This right here being the origin, and this being the z-axis. And I think it'll be important for this problem that we follow their axis that they gave us. Obviously, the physics is the same no matter what our axis is, and what we call x, y, and z, or where we place the origin. But for this one, let's make sure we follow their lead on it. Because, and I'll read it again, 8 charges, so see there's 8 corners here, okay, of magnitude Q. So a Q, a Q, a Q, a Q, a Q. They all have charge Q. Now, maybe to keep them straight, let's kind of number them. Maybe I'll start at the origin and call that number 1 and go across what I'll call the base here, number 2, number 3, number 4. Then I'll go up here to the top and just go around the horn here, 5, 6, out in front, number 7. That's going to be the magical one here, and then number 8. And then it's right here that this corner, the author labels that and says, call this point A. So point A. Because it says here, determine the x, the y, and the z component of the total electrical force exerted by the other charges in the charged location of A. And then B, what is the magnitude and the direction of this total force. All right, so visualizing it might be kind of the hardest piece here. But let me start off with an extremely important concept that whether you do this problem or not, and, you know, if you're still watching, let me point out that I tried to convey throughout this chapter, here's kind of the gist of the chapter, is if we know how to get the electric field from a point, which we do, I'll write that down here. It's Coulomb's constant times the charge that's making the point divided by the distance from it squared, okay? then everything then can be thought of as a bunch of points, even a continuous objects. Of course, then we would add up an infinite number of really tiny points, so that's where calculus would come in. This would just remain as a summation, so this is supposed to look more like a capital Greek sigma here. So this is the summation of a bunch of points. And so what we would want to do is to figure out the total electric field at this charge number 7, and it would come from the other charges. The charges 1, 2, 3, 4, 5, and 6, and then 8 would all make an electric field at point 7 or point A, and that's how we would get the total electric field. Now, the easier step is once you get that electric field, you can then figure out how much force is on that charge, and in this case it's number 7, by then taking that total field, which is made up of the 7 other pieces, and then multiply by the charge you're putting there, which in this case would be charge number 7. So these are our 2 big steps, and this is the lesson of the whole chapter. So if you have come this far, I hope that much makes sense to you, and you should know that. If you've gone through this week, or this is the big picture that you should have gone out, that conceptual idea that we want to find the force on something, we multiply by the field. The field's made out of a bunch of points, so you just add up all the points to get the field. And it really is that simple, at least it's simple in words, and then of course when you actually try to do the arithmetic and or calculus, it's difficult. All right, so know this then. I am going to then solve this by saying, all right, what is the total field at point A? Then, of course, once I get that, I would multiply by the charge, and I would get the total force. And then B goes on to get the magnitude and direction here. But I'm going to go ahead here and say that I would do something along this. Maybe I'll write it out as electric field 1 plus electric field 2 plus electric field 3. And so this comes from charge 1, 2, and 3. Electric field number 4, electric field number 5, electric field number 6. And we're trying to find it at 7, so we're not talking about the field from itself. And so the last one here, let me call field number 8 from charge 8. So 1, 2, 3, 4, 5, 6, 7. So there it is. To get the total field at point 7 or point A, I add up the field from the other charges. So it would be 1 through 6 and then 8. Okay. So setting this up, really more visualizing it might be the challenge. So let me go through this one by one. Why don't I start with E1. Now E1 can be actually a pretty hard one. Actually E1 might be the hardest one. So because of that, maybe I'll do them out of order. Let's build up. yeah. Let me. Oh, I'm out of paper here. Let me build up. Let me grab some more paper here. All right. Let me not do E1 first. That was not where I want to get started. All right. Let's start with an easier one. So if we're looking here. One of the ones that I think would be very simple is just number 8, okay? Now, they said the size of the cube has length S. All right. So I'm going to do field number 8 here first. Okay. So field number 8 would be Coulomb's constant times the charge of number 8. Now, they all have a charge of Q, okay? And then the distance away, so this would be S squared. And it would point away from the charge if it is positive and towards it if it is negative. All right, so let's say it's positive. If it's positive, then at this point right here, and maybe a slightly different color could be useful. Let me go to green. That would actually be quite a bit different in color. Even though that's not the same color your author uses for the electric field. Hopefully it'll stand out on the video camera a little better. But that would be directed on the y-axis, okay? Now, if it is negative, it would be directed inward. So what I'm going to do is I'm going to just put in my little equation here j hat. Because if q is positive, then this is saying it points in the positive, because these other ones are positive, so positive times positive would be the positive j direction. But if q is a negative number, then I'd have positive, positive, and there's a q negative, and so ultimately that would be the negative j direction. So I'm not saying whether q is positive or negative, so that's the good thing here. But what I am saying is I need to put into this equation the value of q, either say like a positive 2 or a negative 2, and it'll give me the appropriate vector direction right here, or the plus or minus with the j hat. So note that, you know, that's kind of nice. So that's the easy one. Another easy one is straight across, it's number 6, okay? And so by the same logic, number 6 would have Coulomb's constant, a charge of q, a distance of x squared. And the same logic, it would be pointing outward. Now, maybe at this point, I ought to get a three-dimensional object, and I see over here in my lab equipment, I've got this nice little box of chem wipes. All right, maybe I'll hold it here upside down and maybe even angle it so you can kind of see it's three-dimensional here. But maybe if I hold it this way, and of course down, so down here is the origin, okay, and we are looking right here. So number 8 was right here, and so I'm just starting now with number right here, number 6 on this corner here, okay, and so it would be pushing this way in the x-axis. So in my drawing, it would look something like this. It would be pushing out that way, okay. So in my calculation, that would be an I hat direction, okay? So, again, here is the point I want to know, and so here's number 8. It would point that way or that way if it's negative. And then from this charge over here, number 6, it would point that way or back that way. But again, that's what that negative would do. So if q is a positive number, it would point in the positive I hat direction, and if q is a negative number, it would point in the negative x hat direction. So this is valid whether q is a positive number or a negative number. So that's good. All right. So those are what I'd say the two easier ones. Let's look at number 5 here. Okay. And number 5 is going to be a little tougher, but not too bad. And so number 5. Number 5, again, would be Coulomb's constant times q. And the distance away, well, here's how we're going to have to do Pythagorean's theorem, because it's along the diagonal in this picture here. If I bring back the real three-dimensional object, we're talking about, here's charge number 5, and we're trying to find here at 7, so it's across this diagonal. And of course, if this is an s and this is an s, I would have s squared plus s squared equals this squared. Okay, so that would be 2s squared. So this distance squared is 2s squared. I guess you could write it if you want as s squared plus s squared, but that's just 2s squared. Okay, so that's the magnitude of number 5. But we need to make it then into its components. All right. Now, remembering a little geometry, this then would point out, and it would be then at a 45 degrees. And so, hard to visualize maybe in this picture, but pointing straight out this way. And the cosine of 45 would give us the x component, and the cosine and sine of 45 would give us the y component. So what I'm going to do in my math here is say, okay, so this is the magnitude of number 5. If I go cosine of 45 degrees and multiply by I hat, and then sine of 45 degrees and multiply it by j hat, those would give me the two components. And by the way, the plus or minus for the q still is valid like it was in these other two. Okay, so there would be an, a x component, and there would be the y component. All right, so those are the ones that are in the same top plane as number 7. And like I said, those are probably the easier ones. They're definitely the easier ones, okay? But I should have started there. All right, now let's go to these on the bottom. And again, not doing it in order, but actually number 3 is going to be pretty easy here. Number 3, and so E3, again, would be Coulomb's constant times Q, and the distance away is just S squared. It's directly below it. If I bring back my little cube here, we're talking about number 7 here at the top, and then maybe I'll just turn, but number 3 is right there. Okay, and it's this an S distance away, and its field would then point straight up, and so that'd be the Z direction. And so this would be a K hat direction. Okay. Continuing on, maybe coming back to the picture, maybe we'll look at the field from this one right here, number 4. So E4. Okay. Now, E4 would, its distance away would be along this diagonal, and here it would be like this, right across that diagonal. And I know mine's not my box isn't a cube here, but you got to kind of imagine this being a cube. So that'd be along the diagonal. It'd be the same length as this one, okay? And so that would be an S and an S, and you'd square it. So S squared plus S squared would equal this squared. And so as I try to find the field from here, number 4, at this location here, number, at point A, or number 7, we would go Coulomb's constant times Q, and just like we did for number 5, it would be a 2S squared. Okay, so it'll be kind of along here. Now here you got to kind of visualize, so hold it this way, but it would come up at, at a 45 degree. So the cosine of 45 would give you this dimension, which would be the y-axis, and the sine of 45 would give you the k direction. All right, so cosine of 45 would be the j hat direction, and sine of 45 would be the k hat direction. Okay, well, continuing on, and let's go to number 2, which would be a lot like number 4 here. You would come across this diagonal here. And so electric field number 2 would equal, okay, so let's see. If I hold it back in this spot, so we're trying to find the field here, and we're trying to say it's coming from this one over here, number 2. And I think you can see how that would be very similar to number 4 here. Okay, so number 2 is over here. It's going to make a vector off at an angle like that, 45 degrees. And so cosine of 45 degrees would give you an x component here, an x component here, and sine of 45 would give you a vertical component. Okay, so let's see. Coulomb's constant times Q, and its distance squared would be 2s squared. Okay, and so if I go cosine of 45, you got to think about this again. Okay, so turning it this way, because we're going to be pointing up like this. Okay, so cosine of 45 gives you along this axis. That's the x-axis. Okay, and sine of 45. Sine of 45 is kind of this upward piece, and so that's a k hat direction. All right, so finally we get to the one that's the hardest. Excuse me. 1, 2, 3, 4, 5, 6. Yeah, so here's the last one. E1. All right. Now, E1, let's get a good visual picture of this. This is going to be the hard one. Okay, so this is going to be the field created from the one at the origin, way over on the other diagonal. So in here, we're saying, what's the field over here at point number 7, coming from all the way over down right here at this origin? So the first thing to do is to find, well, what is its magnitude? Okay. So it's Coulomb constant times Q, and then, ooh, how far away is it? So we're talking about across the diagonal here. Now, we're kind of looking straight at it in my picture, so it doesn't really show its full length. I think from 8 to 2 across this diagonal would kind of illustrate it. I'll use this again, but what we're talking about is how far is it from this corner down here, the origin, all the way over to this point A, number 7. So kind of, you know, across the whole diagonal of this box. And there's where we'll do Pythagorean's theorem in 3 dimensions. That may not be as common to you. And so x squared plus y squared you're probably familiar with, but it also works for z squared when you're doing in 3 dimensions, and that would be the length squared. You can prove that, and I think I will digress too much if I go to prove that, so I'm going to hold off on that. But just remind you then of Pythagorean's theorem in 3 dimensions. So if you're looking at the distance, okay, so let's see, the distance from this corner over here to this corner, you would go up S, and that would be the z direction. You'd come out this way, that'd be the x direction, another S, and you go this way, another S. So you'd have s squared plus s squared plus s squared. So we're talking about 3s squared for the square of the distance from one corner of the cube to the other corner of the cube. Okay? Oh, and I should write it here on the same page. So Coulomb's constant times Q, and that would be 3s squared. All right, now here again is going to get hard. What are the components of this crazy thing? All right, so again, got to think in 3 dimensions. Let me get something that points. Here's what I like to use for my little pointer here. All right, so I've got this old broken mechanical pencil here. But the electric field would be pointing out along the diagonal, something like this in a video. Maybe my cube now is too big for my video camera, but it would be pointing along the diagonal. Back in my drawing, it would look something like this. It would come from one corner, up from the other corner, and kind of stick out. Well, that looks terrible in that drawing, so let me get rid of that. So back to here. It would be sticking out something like this, or at least it would point this way if it was positive, and it would be pointing exactly inward if it was negative. But let's just keep working it's positive, because as we said, this would still work with just Q being a negative number, just make everything go in the other direction. So let's think of it for the moment as being positive here. And you can see then something like this is hard, because it would have a component out this way, which is the x direction. It would have a component out this way, which is the y direction, and it would have a component up and down, which is the z direction. So there's going to be an I hat, a j hat, and a k hat. Okay. Now, I think maybe I will start with the easier of the 3, and it's actually this k hat one. I don't know if you can kind of see here, but this is angled up along the diagonal from this plane, and so it's angled up at 45 degrees. Why don't I just get rid of the box for a moment and just kind of hold it on my paper? If it's kind of angled up at 45 degrees, you can kind of see that right here, this angle here, if you were to take and multiply it by the sine of that 45 degrees, you're going to get this up piece. So that's it for the k-hat direction. Now the I-hat's kind of interesting here. Maybe I'll come over to here, because if I were to multiply this then by the cosine of 45 degrees, I would get the piece that is projected into the plane. So like this. And then that would be coming out at a 45-degree angle from the x and y axis. So that would not be the x component. I would then, once multiply by cosine of 45 to get here, have to say, and if I was doing this being the x-axis and this being the y-axis, and so when I multiply it by the cosine of 45, I get this right here, which is how much is in the plane, and since this is also 45, I got to multiply by another 45 to get the x component. So that would be cosine squared of 45. Now let's run through that again, because it's the same logic for the y-axis, and so this is angled up. So cosine of 45 degrees would give me projected into the plane. And then if I just draw it in 2 dimensions, another cosine of 45 or sine of 45 would give me the y component. So sine and cosine are the same thing. So cosine of 45 projects it into the plane, and then the cosine of that 45, so squared, projects it onto the y-axis. And I think this might be a good place for me to stop, especially since it's not a homework problem. But I think that those of you interested can finish this up, because now to get the total, I just need to run through and add all the I-hats together, all the J-hats together, and all the K-hats together. So we've got one here. There's an I-hat. There's an I-hat. There's an I-hat. And I'm tempted to say something here as I wrap it up. But why don't I circle that in green? So here's an I-hat. Here's another I-hat. Here's another I-hat. And here's another I-hat. 1, 2, 3, 4. Now look at the J-hats for a moment. Grab a different color. How about a blue? All right, so here's a J-hat. Here's one. Here's a J-hat. 2, 3, 4. Okay. And, well, this could get fun with symmetry, but you know what? I think I'm just gonna leave it and say, look, just add all those together now, and you'll get the I-hat, the J-hats, and the K-hats, and then multiply by the Q, and which would just make everything then Q squared all the way through to get a force, and so these would be force, and these would be force, and this would be force when you got Q squared. So you just got to add all those together, and that would give you then the force. Now remember this then, when you're getting magnitude out of all of this, you will get x squared, y squared, and a z squared. And I think that might be the best approach. There's a lot of symmetry here. It's three-dimensional symmetry, and we could make this problem go a little faster and a little easier if we argue from some symmetry. But it's probably a good place to stop now. All right. Take care, guys.